Okay, welcome week two. We're getting so we're in the middle of chapter three, I think, and we got a little bit into chapter three. So we're going to continue on. Last time, obviously, at the beginning here, chapter three, we talked about kind of the different states of matter. So once again, we do have obviously our solid state of matter, where typically for most substances, they are packed in there pretty tight to one another. They don't have a lot of room for movement. They also have not a lot of energy going on, which is why they sort of just kind of lock into one another. We then have obviously our liquid, still fairly close to one another. But they do possess a little bit more energy. Because they possess a little bit more energy, they are able to sort of move past one another while fluid and before they sort of settle into that solid. And then lastly, obviously, we have our gas state. And at the gas state, everybody is, again, he's sort of broken apart from one another. Obviously, has sort of the most energy as they're flying around, causing collisions with either the container or other gas molecules. We'll talk about sort of the transition of state here as we go from solid to liquid. Again, that's the process of melting. Going the opposite process, it's the process of freezing. If we go liquid back to solid, as we go from liquid to gas, that's evaporation or vaporization. Gas back to liquid is condensation. As you go from solid directly to gas, skipping the liquid, that is sublimation. And gas back to solid, once again, skipping the liquid, sort of cleanup, deposition. We talked about sort of the idea of freezing same temperature for what you're doing. The energy in or energy out, not using the normal melting point or freezing point of a substance. Same thing with evaporation and condensation, same deal. That also occurs at the same temperature. Yeah, water, which is one you really should know, as we talked about last time. For water, this is basically 0 degrees Celsius, 100 degrees Celsius, and obviously, if we're talking about water, people have obviously some different temperatures there. In terms of energy, as you go from solid to liquid to gas, those are all processes where energy has. I can think about a very simple example, as we talked about, of the ice cube. If you just take an ice cube out, because energy or heat flows from hot to cold, the ice cube again is colder than the air outside. So we'll just pick up the energy and absorb the energy. And these are all processes that basically absorb energy. And again, in chemistry, as we'll see a lot, absorb energy. That again is what is referred to as an endothermic process. And the opposite is true as we go from gas to liquid, solid. Basically, energy to be released in that case. So if you think about gas molecules around really fast, as they release their energy, they no longer can fly around that fast. So as they collide with other gas molecules, they really won't have enough energy to escape them, and they'll kind of clump together, if you will, and kind of go into the liquid phase. As they continue to remove energy, they will sort of lock themselves up, perhaps into solid phase. And in chemistry, again, when we release energy, those are processes which are referred to as being exothermic. Any questions on any of that stuff that we sort of talked about last time? All right, so continuing on, I think this is where we sort of laid up there last time. We talked a little bit about physical and chemical changes and property. So a physical property is a property that can be measured without really changing the identity of a substance. So when we talk about physical properties, things like odor, color, volume are common physical properties. Most common physical property we come across a lot is the state of something. So is it a solid? Is it a liquid? Is it a gas? Density, melting points, and boiling points are also physical type properties. We could measure again the melting point of ice by heating it and recording the temperature at which it starts to convert to water. But because there's only a difference of states between the ice and liquid water, again, this is more of a physical property. So a physical property and really a physical change really involves around what you start with and sort of what you end with are fundamentally the same thing. So if you're thinking about sort of a physical change, which a physical property obviously sometimes goes with, um, again, uh, you have not fundamentally changed what that substance is in a physical change. So definitely in a physical change, basically what you start with and what you end with is basically the same thing. So ice again is a very good example of that. If you basically do any of those changes, you take ice to liquid water, you put some liquid water up there and you start boiling it and it boils into steam. Ice, liquid water, and steam, they're all different names, but fundamentally they're all the same molecule. They're all H2O. You have not created anything new. It just may appear different along the way. And that's sort of the hallmark of a physical change is, again, although maybe some type of physical property may look different, fundamentally what you started with and what you end with is still fundamentally the same thing. If I took a piece of paper and I ripped it to pieces, it is still paper, right? It's just in a lot of pieces, right? So that is, right, a physical change. Now, clearly, if I burnt that paper, and then I'm creating a chemical sort of change that will occur. But if I just simply rip the paper apart, technically speaking, you could tape it back together, glue it back together, but fundamentally, each of those pieces are still paper. Now, in a chemical property, a lot of times when we look at a chemical property, we must carry out a chemical change. And a lot of times a chemical change is definitely different than what we have with a physical change. In a chemical change, basically the opposite is true. What you start with and where you end up, you actually make new things. So fundamentally, you no longer have basically the same thing that you started with. So if you take wood and you burn it, you pretty much have not left. You got lots of other things that you made through that sort of reaction of it burning. Rusting of cars. Basically, you had iron before. Well, iron, some moisture, and some oxygen is all you need for rust to form, but you form now iron and oxygen that have been bonded together to make rust. And one of the key things about a chemical property is basically the ability to go through a chemical change, or even sometimes the ability to resist a chemical change is sort of a chemical property. A chemical change is oftentimes referred to as a chemical reaction. So any type of chemical reaction is typically a chemical change. And one of the main things, like I said, is basically what you start with and what you end with are fundamentally different things. You can't get back the original stuff by any type of physical means. You can't like freeze it, boil it, or anything like that to put it back together. So the formation of water from hydrogen and oxygen uh, is a chemical change. You cannot just take water and like freeze it, boil it, or anything like that and get the hydrogen gas or oxygen gas back. Otherwise, that would not be great if you're like boiling water. The only way you could get it back is you would have to do another chemical change, which is electrolysis of water, which is a chemical change to get back to hydrogen and oxygen.
Yeah, that's exactly what I was
Yeah,
saying.
yeah, yeah. Yes, and again, that would be another chemical change that would be required. And in that situation, again, you know, you end up with something that's different. So the making of water and really the breaking of water is both chemical changes that occur. And again, what you start with and what you end with are fundamentally different things. Again, making, for example, something like a hard boiled egg is a chemical change. In addition, when we eat food, right, it gets processed into a lot of things and broken down into a lot of things that fundamentally are different than the food that we sort of ate. And obviously, those are chemical changes as well. So, again, a physical change, what you start with and what you end with, fundamentally still the same thing. You got a shirt that's wrinkled, you iron it, it's still a shirt, it just doesn't have as many wrinkles, right? You have a shirt and you spill paint on it, and it's technically still a shirt, right? It's just got some different colors on it, or you colored it with some type of marker. It's still physically, the shirt is still a shirt. Um, Chemical changes, again, on the other hand, involve really making new things. So what you start with and what you end with are fundamentally different things. And once again, through traditional physical means, you cannot get back sort of what you started with. Chemical changes, like I said, are usually referred to as chemical reactions. Silver tarnishes by reacting with substances in the air. It goes through oxidation and makes silver sulfide. And again, fundamentally different things. Let's talk a little bit about elements and compounds. An element is basically a substance that cannot be separated back into any simpler substances by chemical means. If you look on the periodic table, obviously, those are all the elements we have. And you should think of elements as sort of as far back as you could kind of go, right? It's like kind of like the alphabet, right? We only got like 26 letters, I think so. But that's as far back as you could go, are basically the elements. Elements are basically represented, as we'll talk about in the next chapter, by atoms, is a basic simple representation of each element. And they have protons, electrons, and neutrons, as we'll talk about. Now, when we talk about an element, it is made up of really atoms of just that particular element. Now, when you look at the periodic table, pretty much all the elements up there come as what is sometimes referred to as being monoatomic, which basically means that they come as one atom. But there are certain elements that do come as diatomic molecules, and diatomic molecules basically means two atoms involved. And those elements, H2, N2, O2, fluorine, chlorine, bromine, and iodide, how they naturally come when they are by themselves is they basically come as twos. So, for example, hydrogen comes as basically two hydrogen atoms together as hydrogen gas, and they are united. That is still an element because, again, the only atoms present are hydrogen in this case. There's sort of a couple words or three words that sometimes people get a little confused on, and the other words and molecules. And sometimes people have sort of a misunderstanding between a molecule and a compound. And let's talk a little bit about sort of the difference between these. So obviously an element is made up of just atoms of that particular element. And by the way, speaking of the elements on the periodic table, just so you know, if you have any of those elements that are by themselves, not combined with anybody else, they do not have charges or anything like that. So they are neutral. They usually come as ones, except for those guys that come as twos. There's no charges. Things, as we'll talk about in a later chapter, really only gain charges when they hook up with other elements. So when they start hooking up with some other elements, particularly when metals and non-metals come together, that is when these things sort of get charges. But if you have a piece of sodium metal by itself, piece of zinc by itself, it does not have a charge. And again, they only sort of gain charges as they sort of combine. So when we talk about a molecule, you can think of a molecule, it's just a basic definition of something that has two or more atoms. So a molecule is basically some substance that has a combination of atoms. Now, those two or more atoms can be the same element. Those two or more atoms could be different elements, but it's kind of like a basic definition of, oh, I got two atoms. They are going to be a molecule, or can be called a molecule. a compound, as we will see, and we'll just kind of talk about it here. A compound is two or more atoms of different elements. So a compound has to have that sort of extra distinction of you do have to have two or more atoms involved, but you also have to have two or more elements involved as well. So, for example, if we just look at basically two sort of examples, H2, as we just saw here, H2 has two atoms together. It is a molecule. All of those atoms are hydrogen, which means it is actually an element as well. But H2 is not a compound. So H2 is not a compound because it only contains hydrogen atoms. So it doesn't have other elements involved. So it will not meet that sort of compound classification. Now, if you look at something else we've been talking about, which is our friend water. So water is basically two hydrogen atoms and an oxygen atom together. And it has definitely 1, 2, and 3 atoms. So it meets the definition of a molecule. There are atoms of oxygen and hydrogen involved, which means it also meets the definition of a compound. But it does not meet the definition of an element because there's two different elements involved. There's hydrogen and oxygen in this case. So that's the key difference. Like I said, you kind of think of a molecule definition as just a basic thing that all you have to have to get yourself to a molecule is two or more atoms. Again, it could be the same or different elements. But in order for it to be a compound, you got to have at least two or more different elements involved for it to be classified as a compound. Any questions on that there? So obviously, as I just mentioned, a compound has that additional sort of classification of you do need two or more atoms, but you also need some different elements involved for it to be a compound. Again, CO is carbon monoxide. That's carbon and oxygen together, which would be classified as a molecule and a compound. Not to be confused with the element, CO, which is cobalt, and that is just one actual element involved. Compounds, unlike elements, can be broken down through chemical means into elements. So as the example of electrolysis there, if you run an electrical current through water, which I believe we will do in one of the labs coming through, just need a 9-volt battery, I think we do that lab still. If you run that electrical current through it, again, you'll get your hydrogen gas and you'll get your oxygen gas that will start to bubble out there of the water. And again, we go from a compound down to its elements. And again, that's as far as you could go. So you can't go any further than that. Now, the property of compounds are usually very different than the elements that make it up. So obviously, water has very different properties than if you had hydrogen gas or oxygen gas playing around with. They have very, very different sort of properties. Look, the magic of chemistry, right? You got some sodium metal, you got some chlorine gas, and you put that together, you make some sodium chloride, right? Like a salt here. And or even an aqueous solution if you want to put it in that. And we'll do a little balancing here. Sodium is a metal, chlorine is a toxic green gas, but you put it together and you get salt, which has very, very different properties than both of those guys together, right? Nobody would want to put like a piece of metal or chlorine gas on their fries, bless you. But maybe salt's okay to put on your fries. So again, the elements have very, very different properties than the compounds that they make up. That, by the way, sodium chloride is what's known as an ionic compound. It is, again, atoms, two different elements that have come together, and it is held together different than, say, water, as we'll talk about in the bonding chapter. Sodium chloride is held together by opposite attraction, no sharing of electrons, while something like water is actually held together by sharing of electrons. The next thing we're going to talk about are mixtures and pure substances. So a substance or a pure substance is basically a form of matter that has a definite composition. The number and types of units present have distinct properties. So things like if you had pure water, it should all be water. It should all be fundamentally H2O. If you had ammonia, table sugar, or gold, these are all pure substances. Typically, if you look at different substances, a lot of times they have appearances that allow you to, for example, tell it apart. So obviously, if we had water versus some gold, we would be very easily tell the two apart, hopefully. And they can be identified by sometimes their appearance, their color, and some other things. Now, if you take two or more pure substances and you put them together, you make what is known as a mixture. And a mixture is something that when you mix two or more of these substances together, one of the important things to remember is they actually do retain their identity. So although they may not look like, for example, when you make the mixture, that both things are there, they actually are still there. And a very easy example of that is if I took some pure water, which is a liquid, this would be a pure substance. And if I took just some sodium chloride or salt, this would also be a pure substance. Now, if I take both of those together, I will get basically salt water, which is a mixture. Now, if you've seen salt water, which you probably have, or you take some salt, the salt's going to dissolve in the water. And if you look at it, it is just going to look like you got water, like the salt just left and disappeared and did that thing. But the salt's still there and the water's still there. It does make a mixture in this case, and we'll talk about how they're both there and where they're at in this case. Now, when we talk about mixtures, there's basically two types of mixtures that we come across. There is a homogeneous mixture, and that would be like our salt water. So if we take a look at our salt water here, that is a homogeneous mixture. Basically, what a homogeneous mixture is when you look at it, this mixture, everything looks the same throughout. And basically what that means is if you want to think about it, it looks like one sort of layer or state that's there. It just looks like one thing's there. So salt water, once again, if you looked at a glass of salt water, it probably would just look like regular water to you until maybe you tasted it and go, oh, that's pretty salty. You can't necessarily see the salt in the salt water if it all dissolved. And that definitely is a homogeneous mixture. Same thing with, say, sugar and water. If you took a scoop of sugar, one of those little sugar packets, maybe you're at a restaurant, you put it in your water and you mix it, the sugar is going to dissolve in there. You won't physically be able to see it, but the sugar is still there. And again, it kind of looks like one sort of layer. Everything looks the same, and that's a homogeneous mixture. In a heterogeneous mixture, the difference is you could do as much mixing as you want. You will still see different sort of layers. You will still see different sort of components of that mixture. If you took some sand and water, so the sand is a pure substance, water is a pure substance. And when you put those guys together, you will get basically sand and water here. And if you put that like in a beaker, you can mix out all you want. The sand is never going to dissolve in that water. You'll always see the sand basically in there. Take a chocolate chip cookie. That's a good heterogeneous mixture because you should hopefully see the chocolate chips if it's a good chocolate chip cookie, right? And you can definitely see the different layers obviously in there as well. And that is a heterogeneous mixture. So two types of mixtures, homogeneous mixes, everything looks the same throughout. Heterogeneous, you definitely have things that typically don't mix. You see different sort of components of the mixture in there. But regardless of whether it's a heterogeneous or a homogeneous mixture, everybody in that mixture still retains their identity. And you can actually get back the components of that mixture through physical means. So, for example, let's just talk first off on the salt water here. The reason you do not see the salt part of it is basically when something like sodium chloride gets dissolved in water, it will break apart into a sodium ion and a chloride ion. This is what is known as a cation. It has a positive charge. This is what is known as an anion. It has a negative charge. And because they have charges, we might have talked about it maybe last week as well, but pretty much how things interact with each other, how sort of molecules interact with each other, maybe ions and molecules interact with each other, is they interact with each other in a very simple way, which is electrostatic attraction. Opposites are attracted to each other. So positive things and negative things are attracted to each other. One of the things we'll talk about is look at something like water. Water is what is known as a polar molecule. And basically, for our purposes at this point, it means that there is basically two charges that are sort of on water. The oxygen side of water is more negative, and really the hydrogen side of water is more positive. And as we'll talk about in a later chapter, that's due to really unequal sharing of electrons over the whole molecule. So what happens when you take something like sodium chloride and you put it in water and you dissolve it is all the water molecules with their negative side, which is the oxygen side, will surround the positive ion, or like the sodium ion in this case, and surround it. While water's sort of positive side, which is the hydrogen side, will basically do the same thing for the negative ion, like the chloride here, and surround it. And what happens is because there's just so many water molecules that surround those ions, you physically with your eyes can't see the sodium chloride anymore. The sodium ions floating around in there, or the chloride ions in there. So it appears to you like it's gone, and it's completely gone. Now, what happens and why we know, for example, this is just a mixture and is still there, as you will do in a lab coming up maybe next week. When you have this situation where these water molecules basically dissolve these ions or this ionic compound, if you take that, say, saltwater solution and you heat it up, the wonderfully drawn Bunsen burner there, also known as a triangle, and there's a line there, right? And we heat it up. When you heat up water, what happens to it? It starts to yeah, and when it starts to boil, basically that's where evaporation occurs, right? And as you heat up, say, this saltwater mixture, all these water molecules that are surrounding these ions will start to heat up and basically go off as steam as it starts to boil. And what happens when that happens is it actually just leaves those ions basically free to come back together with one another. And they definitely will want to come back together. So, like if that guy was the sodium ion and the chloride ion, now these guys can come back together, and you would actually see, I don't know if it'd be blue, but you would see the salt. And through this process right here, we basically just separated out this mixture back into its original components, even though we could salt part there. Sure, it is still there. From being same thing if you think about the sand and water. You could do a process which is known as filtration. And filtration is a simple process that you also do throughout our experiments, where you use a funnel and you put a piece of filter paper in there. And probably a really good idea would be to have some the funnel, right? So it doesn't go all over the place. And if you take something like your sand and water mixture, which is a heterogeneous mixture, and you pour it through the funnel, because you have that filter paper, what happens is, although on filter paper, you can't really see it with your naked eye, there's essentially holes, if you want to think about it that way, on it. certain sized holes. Yeah. And basically what it allows is certain size molecules, smaller enough to go through those holes, go through, and bigger things get stuck. So when you pour your sand water mixture through here, the sand's actually too big to go through, so the sand gets stuck on the filter paper. And coming through here, you will get your water that will drop through here. And now for this very simple physical process, we have now separated out both components of that heterogeneous mixture, the sand, right? And now we have the water separated from each other. If you wanted to, you could dry out the sand completely and you would have your water on started with it. So we do not actually make anything new when we make a mixture. And basically we have the components of the mixture still intact when it's all said and done. Would that be more of a physical change or a chemical change when we make a mixture? It's a physical change because we can't start with what we end with, right? It may just look different. For these two examples, we can actually get back the components of that mixture in their original sort of forms. We never created actually anything new. So a very common error that a lot of people make is a mixture, like a chemical reaction, especially when they do something like a homogeneous one where they put something in it and it all dissolves and it's like it's gone. So clearly something chemical must have happened in that case. The particular case is actually just the physical sort of change that's happening. Now, a more better way, I guess, or if you were interested in really getting, say, our saltwater mixture, really want to keep of the components or get back the components. If you just did that in an evaporating dish like you will do in your experiment, and you just put the solution in there and you heat it up in a dish, it's open to the thing. When that starts to boil, all the water is just going to go out into the air, basically, right? You're not really capturing it or anything like that. There is a process where you could, if you wanted to really capture both parts of the mixture and get them back, is you could set up a deal like this where you have kind of two flasks there, and let's see here, drop better here. So, and if you put your salt water over here, and this is all a closed sort of situation where you got two sort of flasks, they're connected by a tube, all enclosed. And we typically would want to keep this tube relatively cold. A lot of times you run like water through it or something like that. So if I do this in this closed container and I do start to heat this up, as we just talked about, what's going to happen to the water part here is it's going to start to evaporate and it will become steam. And since the steam has nowhere to go but to follow this tube, as it goes through the tube, it's going to go from the gas phase and get cooled down, which means it'll go from the gas phase back to the liquid phase, and it will go through condensation, as we were just talking about. And it's going to sort of lose energy. And when it does, it will come out on the other side, and it will basically come out back as liquid water like you started with. And obviously, if you continue to heat this at some point on the left-hand side, the only thing that will be left there will be the salt. And now we have the water that we didn't lose to the air by just letting it evaporate off into the air. And we have the salt, which once again would probably be like a little residue there in the actual left-hand salt. Now, again, this process, both components of the reactor. This is what referred to as, you know, you set it up in a nice apparatus with some nice glassware. This is a distillation apparatus, and a great way just to provide something like a home. What are we actually doing in this particular case to allow it to separate this out? We're actually using in their physical properties. So we're actually using differences in their physical. And what I'm talking about in terms of that is between the salt and water. When we think about the boiling point, that's 100 degrees Celsius. So As you heat salt water, all you degrees, water is going to start to evaporate. You need to heat the heck out of the salt, and most likely it will not out phase. It will not boil. It will just start before it does so. There's a difference between the boiling and the water. Differences in properties. It, it, it will. So here we are basically using the differences in physical properties to separate out these two things. And that allows both, again, us to separate out the salt from water. Now, when we look at the filtration, we're also doing the same thing with that. The filter paper, we're using the difference in size of the molecule to create those out. So by physical means, both filtration and distillation are physical processes that allow us to use the different processes to separate out. All right. And that's what we just talked about. Again, distillation and filtration. Here's a much prettier picture of a distillation apparatus. If you close your eyes, mine sort of doesn't look like it at all, but you get sort of the idea there. Again, it's a closed system. We have our salt water over here. We got our basically condenser tube there that keeps it, and this tube again is kept very, very cold, and that allows us again by using that differences in the physical I'm sorry, the chemical problem. Any questions on that there? All right. Little decision tree matter can be uh, mixed together to make a homogeneous or heterogeneous. You could separate them back out to their pure substances by physical means. And again, those pure substances could either be compounds or elements. If it happens to be a compound, you could, through chemical means, get it back down to elements and stuff like that. Any questions on chapter 3? That is done. Yeah. All right. We can go off to the next one, which I think chapter 4. I think we're going next. Okay, so we're gonna go chapter 4 here next, and we're gonna talk about elements, atoms, and ions. So in this chapter, we're gonna talk about a lot of experiments that were done to help us understand sort of the properties and physical parts of the atom. As we go through it, we'll kind of talk about, what you kind of need to know about those experiments. And later on, we'll talk, I think, on periodic table in here as well, if I'm not mistaken. We'll talk a little bit about ions at the end. So let's talk a little bit about formulas of compounds. A compound, as we just talked about, always contains atoms. No matter where you go, is always H2O. May cost you more depending on how it's bottled, but basically it is always the same ratio of elements that are involved. And it always really by mass also has sort of the same ratio. So, hydrogen is about 1.008 grams, oxygen is about 16. So the ratio of oxygen to hydrogen in water is always like 16 grams, so about 2.016 grams are basically almost an 8-to-1 ratio of mass, 8 grams to 1 versus oxygen to hydrogen. Once again, no matter where you get it, if it is water, it should always basically be that component. The chemical formula is what we use to express the numbers of atoms involved in a compound. The formula of the atoms are indicated by their symbols. When you look at the periodic table, we basically have two types of symbols. We have symbols for elements that are one letter, and we have symbols for elements that are two letter. If it is a one letter symbol, we always use it in a capital form. Yeah, so it's always capital letter. If it is a two-letter symbol, the first letter is always capitalized, the second one is not. So always capitalize the first one, not the second. One letter does get capitalized. As I mentioned a second ago, if you write CO, capital C, lowercase o, and you write CO, these are not the same thing in terms of formulas. Again, C capital, lowercase o, is cobalt, which is an element on the periodic table. Capital C, capital O is a carbon and an oxygen together, and that's carbon monoxide. Very, very different things. So if you're in the habit of always capitalizing everything, you definitely don't want to do that when you're writing symbols, because you may be actually writing something that you're not meaning to do. So we do want to use our symbols for our formulas. We also use a subscript, which is the number that comes on the bottom to indicate how many we have. So when we look at something, for example, like H2O, which is a chemical formula, the subscript number, which is the small number on the bottom, always goes to the guy to the left. So this basically means I have 2 atoms of hydrogen, is basically what the little 2 means. Now, very common in chemistry, we don't like to write ones for things, so we usually never write 1 in things. Definitely in formulas, we definitely don't write ones. So if you look at something like oxygen here, and there's really nothing written, sort of empty, if you will, next to it. It basically means 1. So we typically don't write 1 in the formula. So we typically would not write H2O1 or anything like that. So if you don't see a number next to something, it is pretty safe to assume in chemistry that it's probably 1 of whatever's there. And that would also, again, go to the guy to the left. So it could be 2 atoms of hydrogen and 1 atom of oxygen in this particular case would be the chemical formula here. Um, And it's important when we look at chemical formulas, sometimes chemical formulas are sort of descriptive, if you will, and sometimes just like basic formulas. So, for example, if you had something like this, CH3, COOH, or C2H4O2. These are 2 different ways that a chemical formula could be written. And once again here, 1 carbon there, 3 hydrogens there, 1 carbon, 1 oxygen, 1 oxygen, and 1 hydrogen, 2 carbons, 4 hydrogens, and 2 oxygens in this case. Believe it or not, this is both the same thing, the acetic acid, and these are just 2 different ways that a formula is sort of written. If you add up the carbons on the guy on the left there's 2. There's 4 hydrogens and 2 oxygens on the left, and that's exactly what we got going on the right. The difference between these formulas is sometimes, like I said, they sort of give you an idea as to how things are attached to each other. So if you were to draw acetic acid, which is what this is, it would look something like this. CH3, C double bond O, OH. And if you just kind of look at the one on the left in terms of the formula, it gives you a lot of information about how it's connected. You have like a CH3, a carbon and 3 hydrogens, and that's what we see right there. Next to it there, we got COOH, and that is basically a carbon oxygen double bond and an OH. So it gives you a lot of information and sort of how it's sort of put together and how it's connected. The one on the right basically just tells you what's there, basically. So a lot of times you'll come across chemical formulas that basically just kind of tell you what atoms those elements are present. And sometimes you may see some formulas where it'll give you a little bit more information about how things are connected. Questions on that there. So as I mentioned a second ago, the rules for sort of writing chemical formulas is each atom represented by its symbol. Once again, you want to make sure that you write the symbols correctly. To the bottom right of each of those symbols, you use a subscript to indicate how many atoms you have of it. Once again, if it happens to be 1, we do not put the 1 in the formula. And again, if we look at these examples, this would mean we have 1 carbon, 2 oxygens, 1 nitrogen, 3 hydrogens in this particular case for carbon dioxide and ammonia. All right. So take a moment, and for each of these, why don't you write the chemical formula that would work for it? Then we'll talk about it together here in just a second. Okay, so let us take a look at it here. So first off, we're looking for a molecule, which obviously a molecule, right, contains at least two or more atoms that has 6 carbons and 6 hydrogens. So once again, C is carbon symbol, 6, and H6. Once again, we do want to write those little guys to the right of the symbol. By the way, obviously, at some point, if you're not familiar with the symbols that go with elements, you should start getting yourself familiar with most of them that you see there. Typically, if you look at the periodic table, by the way, to the left, to the right, very common ones that we come across a lot. I would say in the middle region, the first couple rows there is ones that we do see. Kind of the first row, and then kind of the right of the second and third row is the ones that we see a lot. We don't do too much with the ones on the very bottom, the 2 rows on the very bottom, but definitely we're going to get into naming shortly and things like that. So again, having an understanding of the symbols and the elements names that go along with them is going to be very helpful coming up really soon as well. If we take a look at a compound containing half as many calciums as chlorine atoms. So I got 1 calcium, that's half of my chlorine, which means I would need 2 chlorines, is a formula here. And once again, nothing written for 1. And the 2 again goes to the guy there to the left. That would be calcium chloride in that case. And lastly, we have a compound that has equal numbers of sodium and nitrogen and 3 times the oxygen. So equal numbers of sodium and nitrogen and 3 times the amount of oxygen would give us something like sodium nitrate. Yep. Other questions on that? Yeah. Yes, it is. Yes, it is. If you get to organic, you will draw a lot of benzene molecules. Other questions? So obviously formula is really important, proper symbols, and again, the subscripts telling us how many atoms we have of it, as we'll later see in a later chapter, also will tell us what is known as how many moles of each of those guys that we have as well. All right, we're going to talk a little about, again, the atom, and as I mentioned, we're going to talk about some experiments that were performed to help us understand basically the basic structure of the atom. And again, as we kind of go through it, we'll talk about kind of what you need to know for each of these sort of things. So starting with atomic theory here, everything sort of started a long time ago with a lot of philosophers with the idea that matter is composed of these very small particles, which were called atomos, and that was later, kind of a forerunner, obviously, to atoms, and means sort of uncuttable and indivisible. And a lot of things became very clear to scientists as we came across the 18th century. They felt that most natural materials were mixtures of pure substances. Pure substances could either be elements or compounds. And as we sort of touched upon a second ago, the law of composition, which again means that no matter where you get sort of the compound, there's always sort of the same composition by mass of these things. So as I mentioned before, something like H2O, there's basically about 8 grams of oxygen for every 1 gram of hydrogen that is present. And again, that's basically kind of like the molar masses there. Oxygen being 16 grams, and since there's 2 hydrogens, each one's about 1 gram or so. That gives you sort of that 8-to-1 ratio, no matter what it is. And it should always come together that way. Atoms and stuff usually always come together, as we talked about, in these sort of whole number multiples of sort of how they come together in these ratios. One of the first sort of ideas of atomic theory, or an important part of atomic theory, is Dalton's atomic theory. And a reminder that when we do talk about theories versus, say, laws, theories may not always be correct in all aspects of it. Some parts may be right later on and may be found that maybe not all of it's right and stuff like that. And that's the same thing here with Dalton's atomic theory. There's certain points of Dalton's atomic theory that through later sort of experimentation, ideas were not found to be sort of correct. And there's some that, are correct. And John Dalton there's a picture of him, was an interesting guy. He never married. He did take the weather every day of his life, so sort of wake up, write down their weather, and record it. One of the things, obviously, you should always take out from this class is he did like to go bowling on Thursdays, so that is the answer to that question when you see it. It's not like, Fridays or Saturdays, so it is Thursdays. But one of the things he sort of was known for was this idea of what we like to call atoms, so this definition of atoms. And let's talk about some of the parts here of Dalton's atomic theory and some of the things that may be not so correct and maybe some things that are correct. So Dalton basically said that elements are composed of these extremely small particles that he called atoms. He said that basically all atoms of a given element are identical and they have the same size, the same mass, and chemical properties. This, along with sort of the idea that atoms are indestructible, are two things that are not so correct. Definitely this one here. Atoms of the same element are not really always identical to each other. And we know this through the existence of what is known as isotopes, which we'll talk a little bit later on this chapter, I think. And isotopes are the same element, but they have different masses. So obviously they are not identical to each other if they are the same element, but they do have different masses. So that's one of the things that are not so correct in Dalton's atomic theory. Again, the idea of also atoms being indestructible. Well, in normal chemical reactions that we talk about in this class, we do have conservation of the elements. So, for example, in a normal chemical sort of reaction, if we start with 4 carbons, what we end up with, we'll still have 4 carbons. They may be in different things, but we won't like lose carbon along the way. We won't change it into some other element. And that's because in a normal, for example, chemical reaction, it's all about basically making bonds and breaking bonds, and that's just electrons basically. So it has nothing to do with sort of the identity of the atom. In nuclear reactions, it's very, very different. What you start with in a nuclear reaction, we don't talk about in this class. Actually, I don't think you guys talk about nuclear reactions till maybe you get to 1B. You do a whole chapter on nuclear chemistry. But in nuclear reactions, what you start with and what you end with are different elements. They actually change from one element to the next. Maybe you start with uranium and you end up with like lead, or maybe you start with uranium and you end up, with plutonium or something like that. So there's definitely not conservation. We are changing actually one element into something else. So that's the other part sort of Dalton's atomic theory that was sort of incorrect. Indestructible, and also that all elements of the same element, or all atoms of the same element, are identical to each other. Now, some things that are correct is atoms of one element are different than atoms of another. So if you had an atom of iron and you had an atom carbon, they are different. They have different numbers of protons and neutrons and stuff like that. Compounds are composed of atoms of one or more element, like we talked about. That's all good. A chemical reaction really involves only the rearranging and combination of different atoms together. We do not change or create any new atoms in a chemical reaction. So everything we study in here, 1A and pretty much all 1B as well, it's all about conservation of those elements. That's why, as you may be familiar with, if not when we get to that chapter, that's why we balance equations, because again, we just don't like start with 4 carbons and end with 3 or something like that. We don't lose anything along the way. You got to have the same amount of everybody on each side. The law of conservation of mass states that matter cannot be created nor destroyed, and that also is this idea that we really conserve the elements along the way. We don't create anything new in a chemical reaction. So when we talk about the mass, if you started with 4 carbon atoms, each carbon atom is about 12 grams. So you got like 48 grams of carbon. You should end up with like a total of 48 grams of carbon because you should still have those same 4 atoms. So you need to know Dalton's atomic theory, the different parts of it, the things that were sort of correct, and some things that are not correct about it. Any questions on that? Now, this is also how Dalton pictured combination of atoms or compounds. And here you can see in each of these cases, each one of these things basically contains the same 2 elements, right? We got nitrogen and oxygen happening here. But we have different combinations, and actually, as you can also see, different connectivities of each of these elements. On the first one, we have a nitrogen and oxygen bonded to each other. We got 2 oxygens and a nitrogen, and with a nitrogen in the middle. And on the bottom one, we have 2 nitrogens and an oxygen bonded to each other. These, again, are all related to each other, sort of in a relationship of by mass and proportion, kind of the same relationship. So, for example, if you look at nitrogen and oxygen here, NO, and you take the mass of oxygen, which is like 16 grams, and the mass of nitrogen, which is about 14-ish, we'll just round. And you get something like a ratio of 1.14 for the ratio of oxygen. Now, if you come over here and look at this one, which is NO2, the oxygen here, because there's 2 of them, it's about 32 grams, right? And for the not hydrogen, but nitrogen is 14 grams. So if you take your 32 divided by 14-ish, you get about a 2.28, maybe a 9 if you round. But we'll just kind of go in that ballpark. And if we take the relationship between these two sort of compounds, we take a 2.28 and a 1.14, you get a ratio of 2. And this is again how basically he envisioned and how atoms come together. So atoms come together always in these sort of whole number ratios and multiples of how they come together. And just in general, right, you never will have like a half atom, kind of hanging out there or anything like that. So you always get these sort of whole number guys for those subscripts that are on the bottom. So okay, we're going to continue on. So we're going to get to now talking about some experiments, as I mentioned earlier, that help us understand sort of the structure of the atom. I'm going to kind of hit the highlights of the big ones. So let's talk about the atom. Based on Dalton's atomic theory, the atom was defined as really the basic unit of an element that can sort of go into chemical combination. It is basically, again, the representative of really all the elements that are present. That's their basic sort of representation. A lot of experiments were done that demonstrated that although atoms are relatively small sort of things, they do possess sort of an internal structure, and they do possess what are sometimes referred to as subatomic particles. And the 3 subatomic particles that we'll talk about and sort of their discovery and understanding of them, electrons, which are negatively charged. We have protons, which are positively charged. And we have neutrons, which have no charge associated with them as well. So the idea here is we have atoms, which are, again, the basic sort of representation of all of our elements. And within that is a sort of internal structure made up of really these 3 particles. So the first sort of particle we're going to look at is sort of the idea of sort of an understanding of it and some of its properties is the electron. And as I mentioned a second ago, electrons are really negatively charged particles. And really the earliest sort of understanding and experiments that were sort of done to sort of look at, say, like electrons, for example, or the atom, were experiments that were done with a cathode ray tube. And a cathode ray tube is sort of a schematic of it right there in front of us. We have sort of an electrical sort of field set up. There's a negative side. There's a positive side over here. And we have really a beam of negatively charged particles, like electrons. And as we've talked about previously in chemistry, opposites attract. So since our particles inside are negatively charged, they definitely will be moving in this direction away from the negative towards the positively charged plate. When it does so, sometimes they'll put some type of fluorescent material there at the end, and you can kind of see where the electrons hit. Um, a lot of the experiments that were done to sort of understand the atom or explore the nature of the atom, a lot of them were done with a lot of radioactive sort of particles. Three very common sort of radioactive particles that sort of correlate to what we do see in the atom in terms of protons, electrons, and neutrons, and sort of the charges. There are alpha particles. Uh, which are really positively charged radioactive particles. They're really the helium nucleus is essentially sort of what they are. So sometimes people use the alpha symbol. Sometimes people will use the helium sort of nucleus as opposed to that. Yes, sir. Say it again. Yeah, so it's not in this case. Those numbers we'll talk about a little bit later on in this chapter. That's the mass number and the atomic number. What's that? Yeah, it's not positive actually, helium, so it's neutral in this case. Yeah, yeah, there's no charge. So these numbers, as we'll actually talk about them a little bit later on, represent a couple other things. So those are positively charged radioactive particles. Also, beta particles were used a lot in experiments, and beta particles sometimes will use the beta symbol, or sometimes people will use an E for like an electron because it's basically like an electron. It has a negative charge. And then we have gamma rays. And usually people use sort of like the gamma symbol. And they basically have no charge and they're just sort of pure. So these are, three very common sort of radioactive particles that were sort of used to explore the nature of atoms. Here again with the cathode ray tube, we got this sort of charged sort of plates. It allows these certain charged particles like electrons that are negatively charged to move, and you can sort of follow what's going on with them. You may be familiar with a CRT, cathode ray tube. Maybe you've seen it. They don't really make them too much anymore, but really old time TV that has like a back to it, and not like a flat screen. Years and years ago, they used to put them on the floor, those type of TVs. Um, used to call somebody out to fix your picture tube, which is as a cathode ray tube inside there that had a big tube. Or even really older type computer monitors. Have you ever seen one where the back kind of goes out like that? Not a flat one like that. Those are cathode ray tube type monitors. He's called them CRT monitors. Um, but basically, again, as I mentioned, these sort of plates and electrical field, those negatively charged electrons are going to kind of move from away from the negative side to the positive side, and will sort of hit that positive side. And like I said, you can sort of observe where it hits by putting some type of fluorescent material that will fluoresce when it does that. Now, one of the advantages of using something that is charged, like some of those particles, alpha particles, beta particles, and gamma, which actually does not have a charge, is they are affected by electrical fields and also magnetic fields as well. So, for example, if you shot a particle like through this electrical field and it sort of bent upwards here, you would know, since that's the negative side of the plate, that probably that particle is going to have more of a positive charge as it's going to kind of be attracted to the negative side of the electrical field. If you shot a particle through and it maybe bent towards the positive side of the electrical field, you would probably know that that guy is more of a negatively charged particle, again, going to be attracted towards the positive part of the field. And if you just shot one and just kind of went straight through, was really unaffected by any of the electrical field or magnetic field, you probably know that maybe it doesn't have any type of charge associated with it. Otherwise, it would kind of go up or down depending what you got going on in terms of its charge. So this is a cathode ray tube. Let's take a look at this. I think this will play, I think.
This is a cathode ray or Crookes tube. It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
So again, you can see there obviously that the beam is affected by a magnetic field and also the electrical field. Like I said before, probably way before all your guys' ages, but used to call a TV repairman out to fix your TV. If it broke, they would open up the back and go in there and fix the picture tube and all that type of things. Now, this cathode ray tube was used a lot by a guy named J.J. Thomson, and this is one of the first sort of experiments you should be familiar with. So J.J. Thomson in the 20th century did a lot of work with cathode ray tubes. And what he was able to basically figure out through his experiments was an important sort of property of an electron. He was able to basically figure out the charge to mass ratio of an electron, and it is minus 1.76 times 10 to the 8 coulombs, which is a unit of electrical charge per gram. So charge to mass of an electron. You don't have to memorize that number for our purposes here, but you do need to know that he did that. And as you can see, there's his cathode ray tube he's staring at. That out of sort of Thomson's experiment came this idea of the charge to mass of an electron. Another really important experiment that sort of happened along the way there that sort of complemented, if you will, Thomson's experiment and a little bit more information about the electron was an experiment that was done by Millikan. And Millikan did what is referred to as the oil drop experiment. And it is pretty much what it sounds like. There's a chamber he used, and it basically has an electrical sort of field, a negative plate and a positive plate. There's a little hole in there where the oil droplets could go through. Basically shot in some oil droplets, atomized them. They went through here, and as they come through the hole there, they're going to drop by gravity and obviously create some friction and gain a charge. What he was able to do basically is adjust the electrical field in that chamber in such a way that basically the droplet just was suspended. It wouldn't go up, wouldn't go down. And essentially, you can kind of think of it, he was able to almost dial in the charge of an electron by adjusting that electrical field. Here's sort of an animation of that, I think. So the oil droplets go in, they drop, he adjusts the electrical field and kind of keeps the oil droplet there. And the major sort of finding that came out of Millikan's experiment was he was able to figure out the charge on an electron. And it was minus 1.6 times 10 to the minus 19 coulombs. So between the two experiments, these were really big experiments in terms of understanding some aspects of the electron. We had Thomson that had the charge to mass of an electron. We also had Millikan here to figure out the charge of an electron. And if you kind of just take both of those experiments together, take the charge, maybe divide it by the charge to mass of an electron, just cancel. From these two experiments, basically the mass of an electron could really be determined in this case. And if we do kind of look at a calculation like that and take both of those numbers and kind of do that calculation, we end up with the mass of an electron here as approximately 9.09 times 10 to the 28 grams. That is a large number, small number. That is a very tiny number, right? So it's a really, really small number. Again, a reminder with the negative 28, we're going 28 places to the left and put in a bunch of zeros. So that is the mass of an electron. You should have an idea of about what the number is. I don't know necessarily you need to remember the exact number for our class here. Maybe for future classes, they may want you to memorize it. But the mass of an electron here came out of those two. So far, the two things you do need to kind of know again is Thomson cathode ray tube got the charge to mass of an electron. Millikan oil drop experiment got the charge. Using both of those experiments sort of outcome the mass of an electron was able to be determined. Now, that moves us to some of the other sort of subatomic particles that we have in the atom, and we're going to turn to sort of the proton and actually the nucleus as well. And a lot of features of the atom was sort of understood as a result of sort of these early experiments that were done. Obviously, it was determined that atoms do contain electrons, but it was also determined that atoms were neutral. So if we know that atoms contain negatively charged particles like electrons, but overall atoms are neutral, that means that there must be some type of positive component there, right, to balance out the negatively charged electrons. And around the turn of the last century there, the sort of accepted model of the atom, or sort of an early model of the atom, was one that was proposed by Thomson. And his model of the atom was sometimes referred to as the plum pudding model. And essentially, he thought the atom basically was this sphere. And within the sphere, you had all this sort of positive charge. So all this positive charge spread out over this sphere. And embedded inside this positive charge, you have these negatively charged electrons. So you have these electrons that were sort of embedded inside this sphere of positive charge. And one of the main things that he sort of said in terms of his model of the atom was that the most of the mass of the atom was made up of these electrons that were sort of embedded inside. The idea here, plum pudding, is sort of like a pudding with some raisins in there. So like the pudding's the positive charge, and raisins kind of dropped in there as sort of like electrons. So this is, again, an early model of the atom, which you should be familiar with, which is known as the plum pudding. Again, sort of this positive charge really kind of spread out all over the atom, these electrons sort of embedded inside. And again, according to this model of the atom, most of the mass of it is those electrons. This was all good to go, but much like a lot of things in science, I mean, until the next guy does sort of an experiment, maybe it doesn't sort of back up sort of what was found. And the next really major experiment that was done was Rutherford. And Rutherford was a few other guys like Geiger and Marston, like the Geiger counter there, if you ever use anything with radioactivity. Did the gold foil experiment. And the gold foil experiment used those sort of radioactive particles that we talked about earlier, which was alpha. Those alpha particles, which was again those positively charged radioactive particles that were used in this experiment. And essentially, what he did was he shot alpha particles at pieces of gold foil and other metals. And what he expected to happen and sort of what did happen were kind of two different things. So if you think about sort of the early model here of our atom, which is our plum pudding model, we have this positively charged sort of sphere. And what Rutherford was doing was he was going to shoot these positively charged radioactive particles, sort of heavy, and they're moving really fast. So obviously positive shot into a pudding of positive charge. They would expect sort of, and what they expected was these particles would go through and there would be some deflection a little bit as they pass through there. So you can kind of think of it like if this was all the positive charge within the atom, and like I held this really tight on one side and I held it tight on the other side, and somebody shot like a pen right really fast, it probably would be able to punch through the other side, right? But it would kind of deflect a little bit as it punched through the side. And that's sort of what they expected to happen when they did their experiment. What they actually found when they did their experiment was something a little bit different than what they sort of expected based on this plum pudding model. And what they found was, actually, we'll come back to this here in a second. What they found was that in most cases, those alpha particles, went through with really no deflection. So they just kind of sailed right through, no problem. But what they did notice was every so often, they would have this alpha particle that would bounce off at these really large sort of angles. They may even come back to sort of the source at what it was shot at. So, instead of just sailing through, it's coming out at these angles, it's coming back, kind of like if you shot a gun at a piece of paper and having sort of the bullet bounce back at you. That's sort of what they experienced in this case. And that was really surprising to them because they felt like, they all should kind of go through with some little bit of deflection as they're moving through there. So what that made them think about was maybe this plum pudding model was not so good, this sort of earlier model that they had. So maybe that plum pudding model was not so good. And they tried to explain sort of what happened in their experiment by just thinking logically at it. So if I were to shoot these alpha particles, or if you want to take like my pen example, and I just tossed it, and it just went straight, never deflect anywhere, that probably meant that there was nothing in its way, right? So if I took a pen, I could just toss it that way, and it's just going to travel in a straight line, provided I could throw it in a straight line, and it's not going to hit anything, right? So it's just going to continue to travel straight. So what sort of made them understand why most of them just travel straight was they really didn't run into anything, right? So they just basically hit empty space. But they were able to sort of recognize that every so often these things would bounce off at these really large angles. And since these alpha particles are really, really positive, that meant that they had to hit something that was what type of charge? If it made this alpha particle bounce off at these large angles, it had to be very positively charged, right? So it had to hit something that was very, very positively charged to bounce off at these really large angles. So what they had to do was sort of throw away the plum pudding model and go, maybe that's not so good of a model of the atom, and sort of come up with sort of the modern version of the atom, which is the atom is mostly empty space and it does contain a very, very positive core, which was later referred to as the nucleus. And if you just think about my paper example, if this was the positive charge spread out all over, like I said, if we kind of held it really tight and popped something through it, it would be able to go through. But if you took this paper and you folded it, however many times you could fold it, where they say 7 times, 6 times, 8 times, before you can't fold anymore. And if I took all this, and this is now my positive charge, right, all basically condensed into one area, and I try to throw a pin at it, it's just going to hit it basically and bounce off, right? It's not going to be able to just kind of pop through, and it will bounce off. And that's sort of the idea of what they found. So take a look at sort of a little animation here or video of that. There it was. Oops, come here. It's this one.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electron. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So as you can see here again, most of them not having too much trouble, but again, every so often we got these guys sort of scattered at these large angles, hitting that really dense positive core. And again, as I mentioned, it basically forced them to sort of really move away from this plum pudding model. This is sort of what they expected to happen on the left. Those guys kind of bounced through with some deflection. This is sort of what they saw on the right. And come up with, again, as I mentioned, sort of the modern version of the atom. So the new sort of version of the atom is the atom, again, is mostly empty space. And that basically accounts for why most of those alpha particles had no problem kind of sailing through, because basically didn't run into anything. It does contain a very positive core, which is the nucleus. And as we know, within the nucleus, why it's positive is that really is where protons are found, which are positive. So we do find our protons or other sort of subatomic within the nucleus, which are positively charged. Later on, in like the 1930s, neutron is also was found to be in there in like the 30s. It has no charge. Uh, and again, that accounts for why we see those alpha particles bounce at these really large angles, because again, it's hitting this very densely proton-rich area of the atom that's bouncing off at these really large angles. The other really major difference between the plum pudding model and really the modern version here of the atom is the mass of the atom. And unlike the plum pudding model, where they said that most of the mass of the atom was the electrons, here, most of the mass of the atom is the nucleus. So it is the nucleus that really makes up most of the mass of the atom. Outside in that sort of phase is where you find electrons basically flying around. As we will talk about, electrons don't fly in circles; they fly pretty randomly about the nucleus. Is there any attraction between electrons and the nucleus? Should there be some attraction? There should be, right? The nucleus overall is positively charged. Electrons are negatively charged. There is an attraction. That's one of the reasons why, right? The electrons just don't fly off, right? Because they're kind of pinned to the nucleus by that attraction. Also, as we'll talk about in later, that is why there are certain electrons that are involved in bonding and certain ones that are not involved in bonding, depending on how close they are to that positive attraction, and it holds them tighter. Core electrons versus, say, valence electrons, which are a little further out. So again, here you need to know Rutherford's experiment, what he did. You also need to know sort of what they anticipated would have happened with this experiment, and obviously what they did find happen, and the result of it, which is really sort of the modern version here of the atom, of how we get to it. Any questions on that there? This is just a little table of some of the experiments we talked about and sort of the major sort of outcomes that sort of came from it, as what we sort of discussed there through those things. Now, as I mentioned before, the proton, which is found in the nucleus, and again is positively charged and in the nucleus, it was determined that it has a mass of 1.67252 times 10 to the minus 24 grams. If you remember, our electron was in the ballpark of 9.09 times 10 to the minus 28 grams. We could see that, as we talked about when we did just scientific notation, the smaller negative exponent is actually so the proton is actually much heavier than an electron. It's about 1,800 times heavier than any electron that's basically flying around. That also sort of reinforces the idea of Rutherford's idea that the nucleus, not the electrons, but the nucleus where protons are found, is the most of the mass of the atom, because any proton is about 1,800 or so times heavier than any electron that's flying around. So again, that sort of forces that idea. Now, at this stage, you could think of the atom as follows. The nucleus is comprised most of the mass of the atom, but it is a very small volume. So you could think of the atom, for example, as a big football stadium, Superdome, for example. Scary seats. You're sitting in your seats, you feel like you're going to fall over in the sitting position. But if you think like any big football stadium, you can think of that as the atom. Like on the 50-yard line in the middle is like a marble of basically the nucleus, is sort of that idea there. So although it is a very small volume of the atom, it does make most of the mass of it. Protons, again, are in the nucleus. Electrons are flying out and about from the nucleus at some distance. For a lot of years, it was really thought that in addition to the protons, which are found in the nucleus, there is another subatomic particle, which is the neutron. So in 1932, a guy by the name of James Chadwick did a lot of experiments with, say, alpha particles and beryllium. And what he noticed was there was some radiation that was coming off of these guys that looked very similar to gamma rays. And if you remember, gamma rays is those radioactive particles that is neutral in a sense. And he basically described these particles as being, and he named them neutrons. And neutrons have a mass of 1.67495 times 10 to the minus 24. If you compare that to our proton and why they take it out so many digits there, just barely the neutron actually is slightly heavier than the proton. So out of all three of those subatomic particles, protons, electrons, and neutrons, it is the neutron that is just slightly heavier, or the heaviest one. The proton is pretty close to it, and then about 1,800 times less massive are those electrons that are flying around. This also, again, reinforces the idea of Rutherford's model of the atom, that the nucleus is where most of the mass of the atom, because within the nucleus, you have both protons and neutrons, and each of them individually are about 1,800 times heavier than any electron. So most of the mass is basically residing in that nucleus where you find protons and neutrons. And here again is sort of a comparison of them. Again, heaviest, next heaviest, and the lightest of all of those subatomic particles. Now, for our particular class here, like I said before, you don't necessarily need to know the exact numbers for each of those. I will say maybe as you continue on, they may want you to know them. But you do need to know the order in terms of which particle is the heaviest, which one is the lightest. So you do need to know sort of in that order. But you don't have to know necessarily for each of these questions. But again, like I said, you know, for those experiments that we talked about, pretty much the experiment done, how it led us from one of the early models to one of the models, our current model, the modern version of it that came out for Rutherford. So those are sort of the things you. All right, so let's talk a little bit more about the atom and some other parts of it. Here's sort of a cross section of a atom. Again, you can see the nucleus there in the middle where we have protons and neutrons, very small. The kind of pinkish area there, not so pink on that screen, more reddish area on that is basically that empty space. And that is where the electrons are flying around. That's actually kind of like what is sometimes referred to as an electron density map. Not turning out very great up on the screen, I don't think. But what it really is kind of darker pink in this spot. And as you sort of fan out, it's a little less pink. And basically what that is we'll talk about in a later chapter, is the idea of probability of finding an electron in that area. So you can see the darker area is a higher probability of finding an electron. You can see around the nucleus is much, much darker. And that means there's a much higher probability of finding an electron in that area. Again, because of that opposite attraction. Once again, as we will talk about in a later chapter, not necessarily we know exactly where it is or how it's moving, but just in terms of probability, the chance you could find an electron there. As you sort of fan out and get lighter, sort of pink, the probability to find an electron sort of decreases. Doesn't mean you cannot find an electron out there, just probably a lower probability because it's farther away from the nucleus than you would be if you're like standing, you know, next to the nucleus. All right. Now, the chemistry of atoms comes from electrons, and in reaction we talk about in this chemistry class, we talk about, as I mentioned before, it's all about really bonds being made and bonds being broken, and that's really all electrons. So it has nothing to do with the nucleus. And as we'll talk about here, it really is nucleus, protons, and really protons, but what's in the nucleus that is most important in terms of what element you're dealing with. So because in normal chemical reactions, we don't touch anything in the nucleus, that is, again, why we have that conservation of elements in a chemical reaction. 4 carbons to start with. We end with 4 carbons. Let's talk about some properties of atoms: atomic number, mass number, and isotopes. So we're going to start with the atomic number. And the atomic number is sometimes abbreviated with a Z. And the definition of the atomic number is the number of protons that you have in the nucleus of an atom. So the atomic number tells you how many protons you have in an atom. If the atom is neutral, then it will also tell you how many electrons you have, right? Because if you think about the three particles we have protons which are positive, we have electrons which are negative, and we have neutrons which have no charge. So the only thing that could affect really the charge of an atom is either the protons or the electrons, since they both have charges. Neutrons obviously have no charge, so it doesn't really matter in terms of the charge. Now, if it is neutral, you should have an equal number of protons and electrons. So if you have a neutral atom, the atomic number will also tell you the number of electrons. It is a very important note that if you are asked a question of, give me the definition of atomic number, the definition of atomic number is only the number of protons. Okay, so the definition, if you're asked that type of question of what does the atomic number tell you, it is just the number of protons. The added information you could get from that is if you happen to know it is neutral, then it will also tell you the electrons. But straight up question, what is the definition of atomic number? It is just proton. The good news is we can find the atomic number right there on the periodic table. It is that number that is typically above the symbol on the periodic table. So for hydrogen, it is 1. See, helium, it is 2. Lithium is 3. Beryllium is 4. If you look at the periodic table or any periodic table, look at all the numbers that come above the symbol. Do any of the numbers repeat on the periodic table? Any numbers repeat up there on top on the periodic table? No, they do not. And that's really important because every single element will have its own atomic number. And since the definition of atomic number of protons, if you had to take a guess as a proton, electron, and neutron, which particle is most important in terms of what element you're doing? It is the protons, right? So if you know the protons, or if you know the atomic number, which is basically the same thing, all you need is a periodic table, find that number up on top, and you know exactly what element you're dealing with. Alternative to that is if you know the element and want to know how many protons somebody has or its atomic number, just go find the element on the periodic table, take the number up on top. So up on top, always the atomic number. So for example, there we look at here nitrogen, we take a look at nitrogen there on the periodic table. Right up there is on top, which is a 7. That means in a neutral nitrogen atom, by the way, I know it was neutral because if I were to see a symbol and there is nothing written on the top right of it, there's no positive charge, no negative charge, nothing written up there on the top right, then it's neutral. Yeah, so you can safely assume. If it did have a charge, you would see something written up there on the symbol, top right, a negative, a positive, some type of charge. So that would mean it has 7 protons, which is positively charged. And because it is neutral, it would have to have 7 electrons as well, which are negative. And that gives you an overall charge of 0, because all the positive guys and all the negative things in the atom basically cancel each other out. Any questions? Could I ever have a nitrogen atom with 5 protons? It is. So it would not be nitrogen, right? So we could never have a nitrogen atom that would have 5 protons because number 5 on the periodic table, as is correct there, is boron, right? So it is those protons which tell you what element you're dealing with. And that is why, once again, as I mentioned earlier, in a chemical reaction, we never change elements because it only involves electrons. It never involves protons. That is also why in the nuclear reaction, which again you'll talk about in 1B, it's all about going to the nucleus and changing protons to neutrons, and that's why we don't get conservation of elements, and we do change elements in nuclear reactions. But in normal chemical reactions, which you talk about pretty much in all your chemistry classes, it's only electrons. So what we balance the number of elements start and end with. Another important number is the mass number. And the mass number is the number of protons and the number of neutrons that you have in an atom. And once again here, the mass number is sometimes abbreviated as an A. And one of the important things of a mass number and atomic number combination is this. If you take the mass number, which is your number of protons plus your number of neutrons, and you take the atomic number that we talked about on the previous slide there, which is your number of protons, and if you subtract the two, protons cancel, that is how you figure out the number of neutrons. So if you take the mass number minus the atomic number, that will tell you how many in an atom. When you calculate or give the mass number, the atomic number, number of protons, electrons, or neutrons, they all need to be positive whole numbers. So they all need to be whole numbers when you do that. So that brings up the important when I go to the periodic table and go. Know that this is my atomic number. Is the bottom one my mass number? What do we think? Is the bottom number on the periodic table your mass number? Always put it this way. Once again, atomic number, mass number, protons, electrons, and neutrons all need to be what type of number? They need to be whole number. Not. Those guys up there are not whole number. That is not the mass periodic table. So that is not the mass number. That is what is known as, we'll talk about, the atomic mass. So that is the atomic mass up there, which is different than the mass number. What confuses a lot of people sometimes is when you see a mass number, look at the periodic table. Sometimes the mass number is very similar to the number you see up there. And a lot of people think, oh, I should just like round it off the numbers, the other numbers that are up there. They did some type of rounding. That is not the way to get the mass numbers. So you will have in these type of problems enough information for you to calculate the mass number if you need to. But you do not get the mass number from the periodic table. Only the atomic number comes from the periodic table. Any questions on that? Yeah. Like I said, you'll be given enough information in the problem. So maybe you're given the number of neutrons and you can figure out the protons and you add them together. Yeah. That's correct. We're going to talk about that when we get to atomic mass, but that's correct. It's an average mass of the naturally occurring isotopes for those elements. Other questions? All right. So let's talk a little bit about isotopes that we talked about earlier. An isotope, again, whoa, come back. An isotope is the same element, but it does have different masses. So as we just talked about, in order for something to be the same element, what number cannot change? The number of protons, right? Because that's the atomic number. So number of protons can't change. So what does change is actually the number of neutrons. Because remember, electrons are way less massive, right? So they're like 1,800 times less massive than a neutron or a proton. So it is the number of neutrons that are different isotopes. So they are the same element, but they have different numbers of neutrons, and that gives them different masses. And that, again, is that one of the violations of Dalton's atomic theory, that all the atoms of the same element are the same. They're not the same because they have different numbers of neutrons, the isotopes, for example. Every single element will have protons, electrons, and neutrons. The one exception is hydrogen. Hydrogen will only have protons and electrons. Hydrogen does not have any neutrons. Now, one of the ways that we write symbols for isotopes is what's on the bottom. So maybe I'll write it here so it's a little bit easier to see. We use the chemical symbol. And up on top, we put the mass number. And on the bottom, we put the atomic number. And that's a very common way that we write sort of our isotopes. So if you have a symbol written like this, the number of neutrons, you basically just take the top number minus the bottom number, and that'll give you your number of neutrons in this case. So if we look at hydrogen, hydrogen has one proton and no neutrons. Deuterium, which is sometimes referred to as heavy hydrogen, has one proton and one neutron. And tritium, which is basically the radioactive version there of hydrogen, has one proton and two neutrons. If we were going to write the symbol for each of these, the important thing here is if you weren't sure what the symbol is the protons. And the protons is the atomic number. So this would tell us that the atomic number we're dealing with here is 1. We could just simply, once again, go to the periodic table and find number 1. And that would tell us the symbol we're dealing with is hydrogen. And the atomic number would go bottom left. The mass number, which would be both of these together, added, would be 1 plus 0 is 1. And that would go up there on top. And that would be our symbol for hydrogen. Once again, if you take the top number, which is the mass number, minus the bottom number, in this case, 1 minus 1 is 0, tells you 0 neutrons in this case. So for neutrons, by taking again top number minus bottom number gives us 0 neutrons. If we go to deuterium here, which by the way does not sound anything like hydrogen, right? But deuterium, you may go, I don't know what that is. But if it did tell you that there is one proton, what you know from that is that number. So you go to your periodic table, find number 1, and the symbol for deuterium is still H, as it is because proton. Atomic number on the bottom. Mass number, going to take our protons plus our neutrons, which is 1 and 1, which is 2. And that's going to give us a mass number here, and that would be the symbol for deuterium. Once again, it gives us 1 neutron. Again, you go to tritium here, which again doesn't sound much like hydrogen, but you see it has 1 proton. Tells me once again, atomic number is 1, and that means the symbol is still going to be hydrogen. And for tritium here, 1 plus 2 will give us our mass number of 3. And again, if we take our mass number minus our atomic number, we end up with 2 neutrons. So all 3 of these guys are the same element, even though they have different names. They are all the same element because they all contain the same number of protons. They all have different neutrons, which means each of these isotopes will have a different mass and obviously are not identical to each other because they have different numbers of. Now, this is a very common way that isotopes are written. Another very common way isotopes are written is something, say, like copper 64. So if I go Cu-64, what does that 64 number represent? Well, if I go to the periodic table over there and I find copper and I look at the number above copper, looks like a 29. I know for sure that the atomic number for copper is 9. It would tell me that the 64 is definitely not the atomic number, which would leave it's probably the mass number, right? So that's a very common isotope written. This number here is the mass number. That means if my copper 64 is neutral, I would have 29 protons, an atomic number of 29. I would also have 29 electrons if it was neutral because they should balance each other out. And my mass number here would be 64 in this particular case, which means that I could also figure out in this case how many neutrons I have, and how many neutrons would I have in this case? Number of neutrons in this case would be our mass number, which is 64, minus our atomic number, which is 29, and you will end up with 35, looks like, neutrons in this case. Any questions on any of that there? All right, so let's take a look. Whoa, super. Take a look at some here. All right, so keep zooming in. Let's zoom out. Try that again. There we go. All right, so take a few moments for each of these, and then we'll talk about it, figure out how many protons, electrons, and neutrons that each of these have. So take a few moments and see what you come up with. Okay, so let's take a look and see. So first off, we have CO here. Again, remember capital C, lowercase o, symbol for an element, which is cobalt. Once again, we do see, for example, in this sort of formula, there is nothing written here, so there's no positive or negative sort of sign. So we do know that it's going to be neutral. So again, remember that the top number here is our mass number. Bottom number is our atomic number. So our number of protons in this case should be how many? 27, which is equal to our atomic number. Because this again is neutral, there is no charge. Our electrons should also then be 27 to balance it out, right? Because 27 positive things plus 27 negative things gives us no charge, which once again is sort of what we got going on in this particular case. That means our number of neutrons, again, is going to be our mass number minus our atomic number, because the mass number is protons and neutrons, and the atomic number is protons. So our number of neutrons in this case going to be 60 minus 27, looks like a 33, I think, in this case. Any questions on that one there? Taking a look at the next one, again, nothing written here, so we do know is neutral. We could take a look at the bottom number, which is our atomic number, and that's going to tell us our number of protons should be equal to it, which is 17. Once again, because this is neutral, we should have an equal number of negatively charged electrons in this case, which it will also be 17. Once again, giving us no charge when we add them together. Our number of neutrons in this case going to be mass number, which is our top number, 37 minus 17. It looks like a 20 in terms of its neutrons. Any questions on that one? Next is, by the way, Cl is chlorine. Last guy there is U, which is uranium. And same idea, we could start with our protons, which is 92, which is our atomic number. Our electrons in this case will also be 92, as it is neutral in this case. Again, nothing written here. And our number of neutrons is going to be our mass number, which is on top, 238, minus 92, which is our atomic number. That's a lot, a buck 46 maybe, 146 going on. So as some of the other questions, typically you will have enough information given to you to calculate the number of neutrons in the problem, or again, the mass number. I give you a period table for the mass number. Questions? All right, let's try a few more here on these. Let's do what it says. Let's write the symbol that includes the mass number and atomic number. Okay, let's take a look. So again, obviously here we can go to periodic table to help us out. So krypton is Kr. And obviously here we're looking for the atomic number and mass numbers. So as we've been talking about, right off the bat, you could get from the periodic table the atomic number, and that's going to be 36. And remember, that is going to go kind of bottom left here of our symbol. What that will also tell us is we definitely have 36 protons in this case. And that's going to be helpful because it told us that we have 48 neutrons. And then remember that our mass number, which is the number we need there up on top, is our number of protons plus our number of neutrons. So in this case, we could take our 36 plus our 48 and get our 84, which would go up there on top left. Any questions on that one there? Next is nitrogen. So once again, you go to periodic table, you find the symbol for nitrogen, which is N. In this case, we also can directly from the periodic table find the atomic number, which is our bottom left. Just like above, that tells us the number of protons is 7. It gives us that the number of neutrons here is 6. So once again, we do not want to use the number on the bottom there on the periodic table for mass number, as that is not the mass number. We want to use what was given to us in the problem to calculate that. So 7 plus 6 will give us our mass number, as that is, again, our protons plus our neutrons in this case. And that's going to get us 13, it looks like, as our mass number. In this type of problem, by the way, as well, it is safe to assume that everything is neutral in this case, as it doesn't tell you it's an ion or anything like that. Lastly, we're looking at iron. Iron is Fe, and once again, we could get our symbol from that. We also could get the atomic number in this case from the periodic table. And in this particular case, they did not give us neutrons, but they did give us our mass number, and that's going to go up there on top, and that would give us our symbol. For this particular one, we are looking for protons, neutrons, and electrons. So our number of protons in this case is going to be 26, as that is our atomic number. It is neutral, so our number of electrons should match. Once again, all of our positives and negatives basically cancel out to 0, right, when you do that. And our number of neutrons in this case is going to be our mass number, which is 56, minus our atomic number, which is 26, and I believe that is 30 in this case, yeah. Any questions on this one here? Questions on how to figure out mass number, atomic number, protons, electrons, or neutrons? All right, but let's talk while we're talking about this about what would happen if we did have something with charges. So if we did have something with charges, sort of what would change. And I think I'll just borrow a couple of things here. I'll just do it up here. Let's look at these couple of examples, I think. So let's take a look at the couple of examples on this page, which is we had our nitrogen, which was 7 and 13. And we had our iron, we'll take the last one there, which was 56 and 26 in this case. So as we just did, as we went through it here, they're both neutral. And as we saw with this guy here, protons would be 7, electrons would be 7, and obviously our neutrons would be 13 minus 7, which is 6. Our guy over here, our protons would be 26. Our electrons would be 26 as well. And our neutrons would be 56 minus 26, which is 30 in this case. So now, what happens if something had a charge? So first off, things with charges, as we will see a lot in this semester, things with charges are known as ions. And ions are things that have charges. And they can either be positively charged or negatively charged ions. And when we have a positively charged ion, that is what is known as a cation, as I might have mentioned a second ago. That is a positively charged ion. And there's also anions, which are negatively charged So we have cations and anions, and we want to kind of figure out, maybe what's going on to give them those charges. So let's take a look at nitrogen here, and let's just say that we had this exact same sort of nitrogen example, except it's going to have a charge of -3 in this case, which is 13 and 7 in this case. So now when we look at sort of what's going on in terms of protons, electrons, and neutrons, our number of protons in this case should be how many? It is still 7, right? Because it is nitrogen. Can I change the protons here to get myself to that charge? I cannot, right? Because as we talked about, out of protons, electrons, and neutrons, it is the protons that determine the element. So if I were to change the number of protons here, this would no longer be nitrogen, right? And obviously I can't have a nitrogen with a -3 charge if it's no longer nitrogen. So you can't change the protons because that changes the element. So protons are locked into place. How about neutrons? Neutrons have no charge, so they can't affect the charge. So the only thing that actually affects the charge is the electrons. And it's the electrons that change the charge or give something a charge. And again, here are neutrons. If we were doing our neutrons, 13 minus 7 gives us 6, just like we had above. Now, in this case, it is the electrons that gives things a charge. How many electrons should nitrogen with a -3 charge have, which is known as the nitride ion? It should have 10. So if you take 10 negative things and you add it to 7 positive things, that leaves you a -3 left over, which is basically where the charge comes from. This guy here, when we compare it to the top, has more or less electrons that it started with when it was neutral. It does have more electrons. The neutral one has 7 electrons. The bottom one has 10 electrons. And this guy is negatively charged. This is what is known as an anion because it has a negative charge. And anions are made by gaining electrons. And the charge actually gives you all the information that you would need to know about how many electrons. So when you look at the number, which is 3, as was just mentioned, that is exactly how many electrons it gained. So when you look at the number in an anion, that is the number of electrons it gained from the neutral atom. The minus tells you it gained electrons, so it's negatively charged, so it's an anion, it gained electrons. So when you see a -3, that means that thing gained 3 electrons from its neutral self. If you see a -2, it gained 2 electrons from its neutral self. If it -1, it gained gained 1 electron. By the way, just like most things, if it was a -1 charge, which it would not be on nitrogen, but if something had a -1 charge, we wouldn't write the 1. We'd actually just write the minus. So you wouldn't see the 1 written either in that situation. So anions are made by gaining electrons. If you just think about it logically, kind of like the little math thing there is, we now have more negatively charged electrons than we do positively charged electrons. So the guy becomes net negative because he has more negatively charged particles moving around. Now, if we go to something like iron over here, and we take kind of the same thing, except we give it a charge like this. We'll go with a +2 charge. This guy has a positive charge. This guy is what is known as a cation because it has a positive charge. And much like the nitrogen example, the protons are locked into place because, again, I cannot change the protons. Otherwise, this will no longer be iron. So it's got to have, in this case, in terms of protons, 26 positive protons. The neutrons in this case is still the same. It is 56 minus 26, which is 30. But now when we look at it, once again, it is the electrons that change in this case. So how many electrons do I need to give me an overall +2 charge? In this case, I would need 24 electrons. If I take 24 electrons, which are 24 negative guys, and add them to 26 positive guys, that's going to leave me my +2 charge left over, because in this case, it actually has now more protons, which are positive, than electrons in this guy. So it's not balanced anymore, perfectly equal. So we now have more positive charge going than we do negative charge. This again is a cation. When we compare our electrons in the positively charged guy to our electrons in the neutral, what we see is it actually has 2 less electrons in the +2 than it did in the neutral. So that is what cations are made, by losing electrons. So when you lose electrons, you become more positive because you have more protons than electrons in you, and you end up the charge. By the way, the charge tells you the same similar thing when you see a +2 charge. The plus means it lost electrons, and the 2 is how many electrons it lost from the neutral atom. Any questions on that? So if you have something that is an ion and you want to figure out protons, electrons, and neutrons, it is just the electrons that are changed. Everything else basically stays the same. And it's those electrons that determine sort of what the charge is, what you got. So for example, if I had a nickel with a +4 charge, and let's just say I had a oxygen with a -2 charge, for each of these, let's do protons, electrons. The bat, our number of protons should be equal to our atomic number, which is the bottom one, which is 28. In this case, we do have a +4 charge, which means it's a cation. Once again, the positive charge means that it has lost electrons and actually lost 4 electrons. So in order for us to end up with that +4 charge that's on there, the number of electrons will be 24. 28 positive things, 24 negative things, leaves us a +4 left over, which is again where the charge comes from. And for our neutrons, we'll take our top number, which would I put there, 60 minus 28, so 32, I believe, in this case. Yeah. Any questions on that particular one there? Taking a look at the next one, which is oxide, oxygen with a -2 charge. Again, the minus right off the bat tells us it actually gained electrons. So our number of protons still going to be 8. Otherwise, again, it would not be oxygen. Because it's -2, that means it should have gained 2 electrons, which would be 10 in this case. 10 negatives, 8 positives gives us a -2 left over, which is our charge in this case. And lastly here, our neutron's going to be 16 minus 8, which would be 8 in this case. So what you could do in this case to figure out the electrons pretty easily, if you want to do it, is if you see the charge like -2, you know it has gained 2 electrons. And in the neutral guy, right, the atomic number would be the neutral electrons, so you could just add 2 to that. And for the cation, +4 means that it lost 4 electrons, and once again the atomic number would be the electrons in the neutral guy, so you can in this case take away 4 electrons from that number and quickly get to the number of electrons that you would have in that case. Any questions on things with charges, how to figure out protons, electrons, neutrons? Okay. So as I mentioned earlier, isotopes, again, are the same element, but with different properties. And one of the nice things about isotopes is because it's really only the neutrons that are different, in most reactions, it's all about, as we've been talking about, electrons. So you can use, for example, as a very common procedure, a lot of times there are radioactive versions or isotopes of elements. So a lot of times in research, people will use a radioactive version of an element. If, say, you're interested in, where something is going or where something ends up, and you could just follow the radiation and it will do exact same chemistry as sort of the non-radioactive version of that element. I used to do research with copper, and we used to use copper 64 and copper 68, which are radioactive versions of copper. And just by following the radioactivity, you can basically follow sort of where the copper ends up, say, in the protein purification process. Let's talk a little bit about the periodic table here. The periodic table, like the one we have hanging on the wall, doors down, there's like, I taught in a class the other day, 3 periodic tables, 2 doors down. They have one there, one there, one there. Feels like periodic table overkill. They took one off the wall here behind me. But the periodic table is an arrangement of elements. It gives a great deal of information. Obviously, some of that stuff we've talked about so far. Obviously, up there on top, we have our atomic number that we see above the element symbol. And again, that is our number of protons. A couple other things. There are elements that are arranged in columns on the periodic table. Those are referred to as groups. Or if you're super old like me, families. Nobody calls them families these days. Most people go with groups. And when you look at a group on the periodic table, which is kind of going up and down, we do have a lot of different numbering. So depending on the periodic table that you may be looking at, you may see upwards of 3 types of numbering up there. You may see what is sometimes referred to as the A numbering, which is the representative numbering. You may also see B numbering, and then you might just see straight up 1 through 18 up there on top going from left to right. I would say in pretty much all the chemistry classes you ever take, and when people just have a casual conversation about the periodic table with friends, thank you for the non-courtesy laugh, I like it. We always use pretty much the A numbering is pretty much what we use in terms of our groups. So the A numbering is this. Group 1 is here. And by the way, group 1 starts with lithium. It does not include hydrogen. So even though hydrogen's hanging out over there, it is not part of group 1. Group 1 does start with lithium. Right next door is group 2. Then we actually skip the whole middle part. And this is going to be group 3, group 4, group 5, group 6, group 7, and group 8. These are basically the A numbering, like 1A, 2A, 3A, 4A. Most people don't include the A when they say it. They just go like group 1, group 7, group 3. You know, they don't really include the A, but they're usually talking about the A numbering. And that is the numbering we will use in this class. And like I said, pretty much all your chemistry classes, those are the numberings that you look on the periodic table. So we have 8 groups that we typically deal with on the periodic table, going up and down. If you go left to right across a row on the periodic table, that is what is known as a period. And a period going kind of left to right. There are 7 periods. 1, 2, 3, 4, 5, 6, and 7. So there are 7 periods going left to right on the periodic table. Those ideally on the big ones, they don't usually put the numbers there, but there are 7 up there. Let's talk about some of the ways the periodic table is broken up in terms of elements. There's basically 3 classification of elements. There are metals, nonmetals, and metalloids, which are also sometimes referred to as semi-metals. A metal is considered a good conductor of heat and electricity. It is usually very shiny. You can hammer it into sheets, pull it into wires. For the most part, all of the metals are solids at room temperature, except for our friend mercury, which on a lot of periodic tables, like you see up there, Hg, sometimes a different color like blue up there, is mercury. Where do we find our metals? On most periodic tables, there is what is sometimes referred to as the staircase kind of coming down from boron. So to the left of the staircase is where we find metals on the periodic table. By the way, the 2 rows on the bottom also are to the left of the staircase. They're also really metals as well along the way. Now, the other category of, or a second category of elements are nonmetals. And nonmetals are found upper right of that staircase. And nonmetals are basically your opposite characteristic of metals. They are bad conductors of heat and electricity. They also have a more variety of states. Some are solids, some are liquids, some are gases. They typically are dull, they're brittle, they're used as insulators. Some examples of gases: nitrogen, oxygen, chlorine. A lot of those diatomic molecules we talked about earlier that are elements like hydrogen, oxygen, nitrogen, chlorine, fluorine, bromine, and iodine, those are all nonmetals and they're all elements and they all come as those twos. Bromine is a liquid, Br2. Solid carbon and sulfur are examples of that. Now, earlier I mentioned that lithium, which is right here, is the first member of group 1 because right above it is hydrogen, right? And hydrogen is actually what type of element? It is actually a nonmetal, but it's hanging out over there with the metals. And on older periodic tables, you used to sometimes put hydrogen on both sides. You sometimes find it on the left-hand side and the right-hand side. The reason hydrogen is over there on the left-hand side with the metals is there's a lot of applications as we go through chemistry where hydrogen kind of, you almost treat it like a metal like in group 1, but it really is not part of group 1. It is a nonmetal. It does by itself come as H2 as a gas, but there is a lot of sort of applications that even though it is a nonmetal, we kind of treat it almost like a metal in certain situations. But it is not part of a group 1. It is not a metal. And again, that is why group 1 does start with lithium here and not hydrogen. Now, the metalloids are sometimes referred to as semi-metals, are the ones that kind of ride the staircase here coming down. And if you kind of think about it, you're going from metals here to non-metals. So our metalloids here are basically elements that have properties that could really fall on either side. So the same element may have some properties that you would look at and go, that seems very much like a metal type property. And that same element may have some properties that we would go like, well, that's also very similar to what you see in non-metals. So they sort of fall on both sides along the way. Is there a question? Correct. So yeah, so it's like a semiconductors and stuff like that. You have some things on that side. So again, those guys are placed on the periodic table in between both of those kind of big categories, and they do have properties that sort of fall on both sides of the thing. Other parts of the periodic table, some of the groups do have special names that you do need to know, obviously. Group 1, which once again, as I mentioned a second ago, starts with lithium. Those are what are known as the alkali metals. Right next door in group number 2, those are the alkaline earth metals. By the way, the word alkaline means basic, and that is where a lot of our strong bases come from, group 1 and group 2 on the periodic table. Things like sodium hydroxide, potassium hydroxide, calcium hydroxide. So a lot of those guys in group 1 and 2, if you hook it up with hydroxide, which is OH minus, you will have a strong base. So a lot of strong bases come from there. Heading to the other side over here, group 7. That's our fluorine, chlorine, bromine, iodine. All those guys that come as 2s, those are halogens. And then the last sort of group that you do need to know the name of, or we take a look at the halogens first before we do that. Halogens, as I mentioned, a lot of those diatomic guys, a variety of phases, gases, liquids, and solids. They're very, very reactive. They also, for example, if you put H plus with them or hydrogen with them, will make a lot of acids like hydrochloric acid, hydrofluoric acid, hydrobromic acid, hydroiodic acid. The very last group on the periodic table, which is group number 8, is our noble gases. Noble means set apart. So noble gases are chemically inert, which means they are unreactive. They will react with themselves, but not other things. And they are a really important group for a lot of things that we'll talk about, but especially, for example, bonding. The whole purpose of bonding, as we will talk about in a later chapter, is for everybody to end up like the noble gases in terms of how many electrons they have. They want to end up in that because they are a very stable sort of situation. Things try to achieve that noble gas configuration in terms of their electrons and make a very stable sort of bond. When we look at the two rows on the bottom, this is the lanthanide and actinide series. If you actually follow the numbers and sort of follow the numbers there, this goes 57, 72, 58 goes right in there. And 89 and 104, there's number 90, which actually goes right in there as well. I've never really seen a periodic table do that. They typically don't do it in books because then your periodic table is wide. The only place that I have seen it, 3 doors down. And it takes up the entire top here of the periodic table because it has to move everything to the right along the way. So that's a lanthanide and actinide series because those are elements where they should follow if you kind of follow the atomic number. If you look between group number 2 and group number 3 on the periodic table, right about here, these are what are known as the transition metals. They are metals, and one of the properties that these metals have is they do have the ability to form multiple types of charges. So, for example, iron could be a +2 or +3. Copper could be a +1 or a +2. Things outside the transition metal region that are metals like potassium can really only do +1. It will never do anything else. Calcium can only do +2. It will never do anything else. But the metals typically within the transition metal region have the ability to form more than one type of charge, except for 3 exceptions, which is zinc and cadmium. It only does +2, and silver does +1 only. But everybody else that's a transition metal can form multiple types of charges. That's also why these 2 rows on the bottom, which technically go where I just talked about in here, they're also sometimes referred to as inner transition metals because they technically should be slotted in the middle of the transition metals as well. Any questions on that there? Characteristic shape, obviously, of the periodic table. They did a pretty good job. They left space and kind of filled in with elements. Things on the periodic table that are in a similar location within groups or sometimes even within rows, if they're not too far away from each other, will have similar properties. As you go from left to right on the periodic table, you're moving from a more metal type of situation this way into a non-metal type situation as you go across and above. First off, any questions on the periodic table? So you do need to know which way groups go, which way rows go. You need to know the representative numbering of 1A, 2A, skip the middle, 3, 4, 5, 6, 7, 8. You do need to know where the special group names are. The alkaline metals are located. The alkaline earth metals, the halogens, and the noble gases are located. You need to know which elements are metals, which ones are non-metals, and which ones are metalloids. Any other questions on that? Obviously, the number on the bottom, as we also talked about on the symbols, those are atomic masses, as we talked about as well. Any questions on that? All right, we're laid up there for today.